వీకోట మండలి దగ్గర వస్తుందన్న, అక్కడే కలుసుకుంటాం. చెరువులో శ్రీగారు సార్ టీచర్స్ ఐడెంటిఫై చేశాం సార్. ప్రకారం చేసి కొంచెం
చూసి
కర్ణాటక వీకోట మండలి దగ్గర వస్తుందన్న అక్కడే కలుసుకుంటాం. చెరువులో
లేదంటే ఎలా కొలుతుంది నువ్వు మనిషిని కదా నేను మనిషిని
చెప్పాను కదా నీ పెట్టు క్యాన్ అయిపోయింది పెట్టు
ఇది ప్రజల తిరుగుబాటు. ప్రజలు కానీ కళ్యాణం చేసి శంఖం పూరించనే రాముని తీరు శ్రీరాముని తీరు సమరం చేద్దామంటూ సైన్యం కదిలించనే హనుమంతుల తీరు ఇది ఆంధ్రుల పోరు ఒక యుద్ధం పుట్టింది సాధ్యం బిల్లబిల్లలాడుతూ పోయింది రమా ప్రాణం నేలను తడిసిన నెత్తుల తిలకం ఎవడొస్తాడు రండిన ఇక మేము అస్సలు సద్దం మీరెవడి దానికి పోటీ శాంతికి మొదలైన గెలుపవడద చూద్దాం
సభకే మన ఎట్లా కాదు ఇప్పుడు
वन जीरो वन वालों ने जब से अमेजोन प्राइम मेंबरशिप ली है ना, कुछ भी ऑर्डर करते हैं सेम डे डिलीवर हो जाता है।
सच में? लेटेस्ट स्मार्ट वॉच
5% कैशबैक के साथ Amazon प्राइम पर।
सच में? ये तो ऑनलाइन रिलीज भी नहीं हुई है।
हो गई है Amazon प्राइम पर।
ये Amazon प्राइम मेंबरशिप सच में टू मच है।
आज ही ले लेते हैं।
Amazon प्राइम सच में टू मच।
करना बुच्ची
ఎక్స్ట్రా నిద్రను తరిమేయడానికి ఎక్స్ట్రా తాజాదనం.
కోల్గేట్ మ్యాక్స్ ఫ్రెష్ ఇప్పుడు 30% ఎక్స్ట్రా.
MongoDB is a document-based NoSQL database. It became very, very popular for its schemaless way of storing documents, because the friction when it comes to writing code has gone compared to SQL-based databases. But I get this question a lot, and I thought this video will be the perfect segue to actually answer that question. What is really the difference between NoSQL and SQL? So I'm going to address that in this video. And but the main purpose of this video is actually going through the evolution of MongoDB internal architecture. So this is a topic that very rarely people discuss because we're going into the bowels of the database, not the front end in a sense that how you interact with it and store data, right? So we're talking about the actual architecture of the internals, right? There's been evolution up until version 5.3. A very interesting feature was added. It's called the cluster collections. So I'll go through this, the evolution of this. So I'll discuss what is the difference between SQL and NoSQL, and in a very deep way. And we'll discuss the first version of MongoDB. Starts with their storage engine, mmap v1, then the Wire Tiger, acquiring them back in 2014, I think, and then moving all the way to the recent changes, which is the clustered collections. And this is all going to make sense by the end of the video, hopefully. How about we get started? All right, so I'm going to use my Medium article, at least the images in my Medium article, to illustrate this. So think of it as like as this slide shows, but go ahead and make sure to follow me on Medium. I started posting a lot of content there. If you like more the written medium than actual videos, but the first thing we're going to discuss is like the database internals. If you look really at any database almost always will have two pieces. And the most piece that we actually deal with and interact with is actually the front end piece of the database, which is the API. You see, the most popular databases API to actually communicate to the database, to tell it what to fetch, to actually ask it to store something, is the SQL language, which stands for Structured Query Language, right? And that is the API that we know and love. And another piece of that, another different API could be like Redis or Mongo, right? So, hey, get this document and store this document. There is no structured query language. There is no selecting tables and fields, right? It's just its own different API. So the API can actually change based on the database. The second portion is actually the data format. When I ask you to get something or I want to store something, what am I giving you and what am I taking back from you? And this is where really a database can shine. It's the core of any database system, the data format. So for the longest time, databases has always been tables and rows and columns, right? And to interact with these rows and columns, you use the SQL language, right, to query it. So when people designed the database back in the 70s or 60s even, right, they thought about it always as, hey, it's always going to be tables and always going to be rows and always going to be columns, and then the application can build on top of it, right? We built it bottom up, if you will. And then so that's one data format, right? But then people challenged this. People came in the 2000 era and says, wait a minute, why do I have to be really fixed to these tables? My application has nothing to do with tables, right? As the web evolved, as the evolution of the web, right, came in, and JSON and documents, really I want to deal with documents. I don't even have a schema per se. I don't have tables with a specific schema. I want to be flexible. Why are you forcing me to do tables? And that's the idea of where documents came in, later graphs came in, later other column-based storage came in, right, instead of row storage. All of this, it really automatically the database became these two parts, where the front end and the storage engine, which is the most important part, the storage engine here. You see? So the storage, once we discuss this, there's the data format, how I'm returning these things to the user, and the user here, I really mean the application. And again, the front end here, I'm talking about the actual database front end. It's in the database, right? Portion. And then the second portion, which is the most important part, is how am I storing the data on disk, right? And the storage engine doesn't really care what you're storing in it. To the storage engine, you have something called a page. And in the page, you have bytes. That's all what it cares about. And the front end part of the database will say, hey, by the way, in this page, there is a bunch of rows, right? I have a row store, right? Where I have a table and I put the row and all the columns. And then right after the final column of the first row, I put the second row. And you can see that it's just if you think of it like an actual page, a rectangle, the first row and then followed by the second row, followed by the third row and all its column, fourth row and all its column, fifth row and all its column, until the page fills. That's why the storage engine has a property called the page size. In AnoDB MySQL, that's 16 kilobyte. In MongoDB, I don't remember MongoDB, but Postgres is 8K, and you can change this page size. So in Mongo, what we're storing is just a document. It's a JSON document that the front end receives, and it turns it into a bunch of bytes, and then we flush it to a page. And it's the same thing. The document, key, the first key, and then the value, and then we just write it to the storage engine. So if you think really, really about it, it's always the storage, what you're storing, and how the front end is actually extracting this information. So document, graph, right, based database. When I say, hey, this is a graph-based database, the storage engine doesn't care. It's just how the front end part of the database actually organizes the bytes such that when I store them, I want to read that page and get as much efficiency in my read as possible. So another piece of the storage engine is indexes, right? Because now we're storing things in a bunch of pages, right? How are we storing them is also another story, right? Are they just a bunch of files? Does each file represent a table or a collection in MongoDB, right? Or am I storing the actual data in the indexes itself? We're going to talk about all that, right? Indexes will help fast track what you're looking for, right? That's also part of the storage engine. The type of indexes you're creating. Is it a gist? Is it a B tree? Right? And all really helps pinpoint exactly what page you are trying to read. Right? So if you have a table or a MongoDB collection, these MongoDB collections just a bunch of JSON documents, right? Storage engine can decide, you know what, this document is really large. I'm going to decide to compress it. So that's all property of the storage engine. The front end doesn't even know that this document is compressed. All it does is, hey, just give me that document. And this part will just decompress it and give it back to the front end, and the front end will return it, right? So there's like a clear separation between these two. And they can share tasks as well, of course. The data files, like where is the actual full data? You know, because indexes only have part of the data, right? It's like I'm indexing on the first name, and give me all. First name is a bad index. I don't know, salary maybe, right? Salary is another data structure we create, and then we traverse it back to get back to exactly to that data, right? To that data file, which then pulls the entire document or row, and then we return it. And you can really be creative here, and that's what people did, right? The storage engine is also responsible for transactions. You know, when I'm changing this and this and this and this and this, I wanted to do it as one unit of work, such that if there is a failure, please roll back all these changes. Don't persist anything halfway through. I want to be consistent. I want to be atomic. And I want to be isolated, my concurrent transaction. All of these are property of the storage engine, really, right? I want durability. I want that if I say commit and you told me the front end, right? That's another thing, right? The transaction will say, hey, I want you to commit. And the storage engine will say, yes, you committed successfully. If I get the success and return to the user, and then later you crashed, that data better be there when I come back, because you told me you committed successfully, right? All of these things, WAL, the write-ahead log, or journaling as MongoDB calls it, right? As I'm writing things, usually when you write things, it needs to go to the data file. That's where the major storage lies, right? Lives. But then writing to the data file is really expensive, because you're writing in pages, these massive pages, 8K and 16K. So imagine like you're touching one column, one property, you need to write a whole page. There is no writing one byte in databases. No, sir. We don't go to disk and say, hey, just change that tiny byte, or just change that tiny 3 byte, or just change that 1K byte. Nope. You can't do that. That's not how SSDs and hard drive works. You have to write in chunks, in big chunks for efficiency. You do an IO, you're going to write in a whole sector. You do an SSD, you're going to write a whole page or a block or a erasable unit based on the new technology of SSDs, right? That's where the shingled hard drives comes into the picture, where they increase the write portions and stuff like that, right? We don't have byte addressability on disk, unfortunately, until today, 2022. We have byte addressability on RAM. You can definitely write single byte in RAM. Definitely, that's fine, right? But on disk, persisted, no, you gotta write in pages, right? And that's what we have today. And because of that cost, right, writing to whole data files, what the data storage engine does, like as you change, all these changes goes to RAM. We call them dirty pages. The moment you touch a page where you have a row or collection or document, we just mark it as dirty. And again, the storage engine doesn't know it's a document. It just knows it's bytes. It knows it's a page with a bunch of bytes that you touched, right? And then you write in memory, and so it's fast. And then later, the storage engine will collect as much changes as possible and then flush it once, right, to the database. All of this is the job of the storage engine. I still didn't come to the difference between SQL and NoSQL, but you will get there. Right? You're clearly gonna see it. I think by this time, if you're still watching or listening, you're probably gonna know the difference, right? So we're not writing immediately, right? We're collecting these changes. You might say, Hussein, but wait a minute, you're writing to RAM? If I commit, you're writing to RAM? What if I crash? That's the problem, right? So that's why, in case to recover from the crash, we create this thing called wall, the write-ahead log. So as we write to the RAM, to these data pages, we also write on disk tiny things that says, hey, here's a journal. On this date, right? Dear diary, on this date, I updated the salary from 10,000 to 10,050 cents. It's a bad year. What do you want me to say? Right? So, and this, on this date, I wrote this. On this date, you just write the changes. So that in case of a crash, we're going to lose the dirty pages on memory. But if I came back, I have all the wall, and I have the last checkpoint on the data file. So I restore that, and I redo the changes. I apply the wall to the data files, and now in memory, I have the final representation as it was when I crashed. Brilliant design, right? Anyway, I'm going all over the place, but the storage engine front end, that is the main pieces. So we talked about what the front end is. We talked about what a storage engine is. The difference between the SQL and NoSQL mainly is this puppy, the front end. The NoSQL guys came in and says, you really restricted me with this tables and columns and this SQL. I hate SQL. I don't like SQL at all, right? I don't like it. And it just doesn't fit our application. I want just to give you a document, just store it. And that's where they redesigned. I think someone came up in one day and shop was like, no SQL. They started a movement. They said, no SQL, no SQL, no SQL, no more SQL. And they created their own technical storage engine. And I believe, if I'm not mistaken, they didn't even have indexes. So say, you guys are so, because when databases, Oracle and SQL Server created, they were just so wired to be, to have tables and rows. And so everything was glued together and sticky. Can't change it. So they created everything from scratch. A storage engine. I'm storing just documents, for example. That's the first use case. I have a document, a JSON document, just store it. It's just a bunch of bytes. Later, they added transactions. Later, they added wall. Later, they have the indexes. They slowly added it. And then the API, just a get and set. The user will get a document, and we're gonna store it on the storage engine. That's it. It's just a bunch of bytes. We're gonna convert the JSON into bison, binary JSON, and then we persist it. That's the only difference. That's the only difference in SQL and NoSQL, right? The data format, which we change it from tables and rows into documents, and then the API, which is the get and set instead of just SQL. And clear separation. And then, of course, there are out-of-the-box storage engines, such as LevelDB or MyRox, right? RocksDB, sorry. RocksDB is a very popular storage engine that does exactly that. It takes a bunch of bytes, doesn't care what you have in your bytes. It doesn't care. It gives you the beauty of indexes and storage engine and all this stuff, right? But then in the front end, you can build your database the way you want. That's why you can build a graph database. So graph will prioritize not rows or columns per se, or even documents, but the traversability. Like, so if this node connected to this node to connect to this node, I want to store them next to each other, right? In this way. And so that the whole goal between the API and the storage end and the front end is that when I do an IO and I give me a page, you want as much as possible that page to have everything you need. You don't want to go back to read more pages. And I can go for ages about this, This just the efficiency of the AI. I think this is the most important thing. But we still didn't get to the main part, which is the MongoDB databases. So now we talked about NoSQL versus SQL. What's the difference, right? Now, what we want to discuss is the first version-ish of MongoDB. This is prior to 4.2. MongoDB first storage engine was called Memory Map version 1, which is literally just a bunch of data files, right? And the data file
నేహా లంచ్ మళ్ళీనా
వస్తుంది అంటే డాండ్రఫ్ తిరిగి వస్తుందా
మళ్ళీ ఆలు పరోటా
డాండ్రఫ్ తిరిగి వచ్చిందా అంటే చవక షాంపూ మరింత ఖర్చు పెంచిందన్నమాట. తీసుకురా హెడ్ అండ్ షోల్డర్స్. ఇది మిమ్మల్ని ఉంచుతుంది 100% వరకు డాండ్రఫ్ ఫ్రీ. ఇప్పుడు డాండ్రఫ్ అంత ఖర్చైనది కాదు, గ్యారంటీడ్.
Right? The data file are stored document after one document after the other. Now, I don't know if there is one data file have per collection. Maybe when you have a collection, you'll have a data file. Maybe it's different. But what's the brilliant design behind the first version was an offset based. That means, hey, I want this document, right? This particular document with an ID. So what Mongo has is a unique identifier, right? If you know about that, and your unique identifier will tell you exactly about this document, right? And there's an index attached to it, right? And this index, this is a B3 index. When you traverse the B3 index, you find the IDs. Like, okay, it's in this page, and then you find it. The pointer of this unique identifier is something called the disk location. I think it's a 32 byte. It's actually 64 bit. Sorry, it's a 64 bit pointer. 32. The 32 bits, the first 32 bits tells you the file name, which file, and the second 32 bit tells you the offset, right? Because now you know which file, but then the file is 1 gig, right? Where exactly is the document in this file is the offset. So with one single read, you can go exactly, because this is how the OS read, right? The OS read will give you the file name, says, hey, go exactly to that location. You can absolutely do that, and the file system allow it. To say, read that portion and read for X amount of bytes, right? So I suppose another property is the document size. So you need to store also the document size, right? So it says, hey, read this part. And then you're going to read that, right? And then you get a bunch of pages probably. And then if you're lucky, you're going to get one document or more, right? That's why the document also have a fixed size. You can't go beyond certain size because of these limitations, right? So now you got it. So you do one B3 scan from the ID, right, to find exactly which document to pull, right? Again, you're going to get a bunch of bytes, and then the front end is responsible to parse the bytes to actually find documents per se, right? And of course, if this was like a relational database, then it's going to be columns and rows, right? If it was a graph, you're going to parse it such that you know the beginning and the end, right? And it's not really rocket science at the end of the day. So we're getting a big O of log n, right? So it's just a one IO or multiple IOs to traverse the nodes. That's why it's important that the B tree is small enough to fit in memory, such that because the index is just another data structure which is persisted on disk. You read it from disk and you put it in memory. Hopefully it fits in memory. That's why Discord actually, one problem that Discord faced was they moved from MongoDB because their indexes were so large they couldn't even fit in memory. And if your index doesn't fit in memory, that means as you traverse, right, the operating system will do these paging and swap files, and will swap things to disk if it's not used, right? And this scanning is going to become slower just to find the disk lock. Okay? But that was the original thing. The clear problem with this is anything you touch, you change the document size, you updated it to a longer string, the entire file is now scrambled, right? Because the offset, you change the physical offset of the disk, right? I suppose you can play with games with this, but this became very, very problematic, right? Because the documents are based on offset. The moment you change the document size, you push it a little bit, the whole offsets are now off, right? That was the original design, I suppose, if I'm not mistaken, in my ISAM in MySQL, which is no longer used because of the same reason. Yeah, it's nice. For read-only, it's beautiful, right? If I'm not changing it, yeah, it's just very fast. You know exactly what it is and you pull it. But as you change it, it becomes really a mess. I suppose you can play tricks. Of course, you can update the offsets, right? You can update the offsets, but that was a problem. Plus, another problem with the mmap is the locking model, right? That's another thing that's the responsibility of the storage engine, really, locking, right? How do you prevent two people from editing the same document at the same time? You shouldn't really do that, right? Databases, no two databases will allow you to update the same unit of work, if you will. If it's a row, if it's a table, if it's a collection, right? In mmap, it was very strict, right? Imagine this, like the first version of mmap was even, they didn't bother. Imagine, because these are people who are rebuilding a database from scratch. So they didn't think about all this stuff that the databases people have been doing it for years, right? For decades, actually. So the first problem they run into is like, hey, two people can change the same the different documents. Oh, the offsets are out of base. You know what? Let's just create a lock, a global lock. So the first version was a global lock per database. So no two transactions can actually change documents in different collections at all. So if you have collection 1, collection 2, you couldn't even change collection 1 and collection 2 documents concurrently. They are serialized. There is one global lock. Again, that was the first version, because it's a single database lock. She says, hey, read these data files. This tells me that the data files are actually collapsed. So multiple data files, multiple collections can live in the same data files. That's one reason. Right? You have to acquire a lock so that no two transaction can change it. But then they improved this in in the version 3s. That wasn't the version 2s of Mongo. In version 2, they made it a collection level lock, which is still not good, right? It's for the SQL people. It's like saying a table lock. Imagine you have a table of 1,000,000 row, and you want to insert a row in the table, and then you want to update another row in the same table. Has nothing to do with each other, right? Imagine these are blocked. Yes, it was blocked. And And if you're using a map, this is still the case. One collection, which is deprecated, by the way, MFv1 is deprecated. Now, one collection is a pair collection lock. So now, sure, you can do a concurrent write on two different collections, right, without blocking. But now, if you're updating the same document, that's a problem, right? So then it became very challenging to manage this storage engine. So what MongoDB did is, you know what, let's just acquire this WireTiger storage engine. Very, very popular, very efficient storage engine. So what they did is MongoDB just scrapped this and they bought a storage engine out of the box. This has become what we call WireTiger, right? And the front end didn't change. So your application code doesn't change. The storage engine in the backend changed, right? So now this is WireTiger. They gave WireTiger the ability. Here's the thing. With WireTiger, the ability of document level locking has become popular. Now you can update two documents on the same collection. I'm now saying these things, and you might say, it's like, this is all exist. I know, but I'm telling you the history of things. Because building databases is not really a trivial thing. The brilliant engineers went through this, and they run into a lot of challenges. And this is one of them. So the WireTiger storage engine allowed you to update two different documents on the same collection concurrently, which is now a beautiful thing, right? Now we can, and this has now made it equivalent to basically all databases, because the databases have row level locks, like at least MySQL and Postgres. You can definitely update two rows on the same table, but you cannot update the same row on the same table, right? We acquire a lock, and then the second transaction tries to update the same row. That will basically pause the second transaction, right? With row level locking. Now there is I think, what's that database called? Yoga DB, if I'm not mistaken. They even introduced column level locking, which is another thing. Like if I have a row and I'm updating field 1 in the row, but you're updating field 2, technically we're not changing the same thing. Postgres will lock you even if you're updating different thing. MySQL, if I'm not mistaken, they will also lock you because it's a row level lock. But now you can also include column level locking, which says, hey, if you touched this row but different field from this row. Same thing with the document, right? I am really just updating this field in the document, in JSON document, and someone is inserting a new field or updating another. Are we locking? Do we really need to lock it? Well, at the end of the day, this is what we do. We lock it. So yeah, if you happen to have two transactions updated in the same row, even different columns, you can't do that unless you have column level locking, right? Or key level locking, if you will, in Nongo, which I don't think it exists. And believe me, when I'm talking about these things, this is not cheap, right? The moment you introduce column level locking, that's another expense, because now you have to keep track of what you're locking. And locks are, guess what, in memory. And raw locks are more expensive than page locks or table locks or collection locks, because you just need one. Versus if you have million and you updated 1,000,000 rows and transactions are in progress, that's 1,000,000 lock, right? Imagine adding column locks to that. So 1,000,000 times whatever columns you're updating. It becomes really challenges, right? Yeah, building database is not trivial. All right, go back to WireTiger. We talked about that. Right, WireTiger introduced compression, which didn't exist, by the way, in MMVB, right? It didn't exist here. WireTiger introduced compression. Now, when you actually take the document, WireTiger compresses the JSON document. So that's really brilliant. Now because especially JSON documents have these fields repeated all the time, right? The field repeats. So you need to compress it. So WireTiger actually compresses that so that's tiny. Why is it tiny? Because now if I'm compressing it, the page will fit more document. One IO will give me more documents than it was a one IO in uncompressed. If one IO uncompressed give me 3 documents, one IO compressed in a single page will give me 20 documents. This is really powerful because now I don't really need to go, if I'm fetching 20 documents in the older models, I have to do multiple IOs. I have to hit the disk multiple times versus in the Wired Tiger, just one, pulled all this stuff, compressed, do a little decompression in the client side in memory, and you get a beautiful 20 documents. The major thing you have to think about here, how do I save IOs? That is the number one job of a DBA, of a developer, of a database. Saving IOs. The less the IO, the faster the database. Nothing else matter. That is exactly what it is.
Finding the perfect dress, strappy heels, and jewelry takes so much effort. पर Amazon पे it's totally effortless.
Amazon पर मिले wear it with suggestions on top fashion brands ताकि fashion हो effortless.
हर पल fashionable.
ఇప్పుడు ప్రాక్టీస్ నాన్ స్టాప్ బూస్ట్ మిల్క్ షేక్ తో
Boost Milkshake, the new secret of my energy.
All right. So now, the way Wired Tiger store the database is completely changed. It's no longer using this disk lock thing, right? Where it's just a bunch of data file and then you have offset, because offsets are really terrible, right? For changing, like the offset changes and you have to update everything. Like what changing one document will screw all your offsets, right? So what they did instead, they stored it as a clustered B3 index. And I talked about this in another video, but I'm not going to go in details. But in a nutshell, right? They have something called the record ID here. And you can basically create anything. This is a hidden index, cluster index into Wired Tiger. And based on the key, you can search. And when you get here, the value is actually the entire document. And not only a document, right? But physically, all the documents, right, are ordered next to each other. So the page that you land on here in the leaf pages are the data. Is the data. This is the data. The entire data is the index. That's what a cluster index says. It's by default what you get for MySQL, not in Postgres, but in MySQL, everything is a cluster index. Every table has a cluster index, and that's how your data is organized around the index. So your table is organized around this index where the leaf pages is the data. So now if you land here, you get the document, and guess what? Because it's on the one page, you get any document before it and you get any documents after it. And because it's compressed, you're going to get a lot of tight documents as well. So you read this page and you get all the documents nearby because it's ordered. Not only that, each leaf page in B+3 is actually linked to the next page and to the next page and to the next page. It's a linked list of pages. So the entire data is right here. So if you find this, if you want to do a range query, it says, find me all record IDs between X and Y. And we're going to talk about what record ID is, because this is not the ID of the document. And that's the problem that Wired Tiger and Mongo introduced in a way. Now, if we have this, if you do a range scan, you're going to get all the documents that are next to each other. So a range scan is really powerful in B+3, especially if it's clustered, because now you're going to get all the nice documents tucked in together, right? So you can find your document using a B+3 search in Wired Tiger using the record ID. But guess what? What is this record ID? It doesn't mean anything to the user. This is an internal thing. But where did this disk lock happen? This used to be called the disk lock, but they changed it. And that's what they had. They had this as disk lock, and their indexes, the ID, the actual user-facing ID document index, has been mapped always to the disk lock, because that's what we had, right? Disk lock. That's exactly this. This is this. This used to be this disk lock. They later changed it to record ID. So it's like it doesn't make sense to call it disk lock. But then this record ID now is just a pointer to where? Not to disk. It is a pointer to this B+3, which is the hidden index. So now if you're actually searching for the ID, the primary key, you're doing 2 lookups in WireTiger, not 1. So actually, ID lookup in WireTiger were slower than the older one, because now you have to search 2 indexes, you have to load 2 indexes in memory, double the space, double the searches, double the IO. You have to write to multiple indexes because you have to sync those 2 guys together. Secondary indexes, not so much, because the secondary indexes, right? If you think about it, really, secondary indexes now just point directly to the record ID. So yeah, in this particular case, all of these indexes always point to the record ID, whether it's a primary index or a secondary index. They all point to the primary key. And that's what's causing us the double search effectively, right? So very similar to MySQL, not quite, because MySQL primary key is actually this thing, right? But the primary key in the first version, at least from 4.2 to 5.2, very recent this change, by the way, right? Until very recently, 5.2. 4.2 to 5.2 is like this, where you search for ID, you find this, and then you do another search, another B3 search. This is not a big O of 1, right? This is a big O of login plus big O of login, 2 searches, right? Whereas this guy, you do big O of login and then big O of 1. Boop. So now we have this beautiful design. The problems we understood. Now the ID is a problem. We have to kind of a duplicate style, right? The record ID is a 64 bits, same thing here, but secondary indexes all point to the record ID. That's the state of art as of 5.2, right? And the ID index is just another secondary index at this point. It's not really a true primary index, right? Because the primary index, by definition at least, is the clustered index, right? It is this one, but we have now double. Now, let's go to the final stage where 5.3, I think, is July of 2022, really. Very, very brand new feature. It's called clustered collections, where you can create a collection and you can make it a clustered collection. That means the WireTiger hidden key disappears, right? And instead, this becomes your hidden index, effectively. This becomes your clustered index. And the ID field is the main focus for this. Now, if you're searching by ID, right, you will immediately search by ID, do a little bit of lookup, and then find the document, because the clustered document is right here. All the leaf pages have your full documents right here. Pretty neat. You don't really need to do these 2 lookups anymore if you're searching for ID. Right? Again, this is an option. It's not, you don't have to do it, right? So if you still want this design for some reason, I'm going to talk about why in a minute. You can still have it. But now, in this guy, you can do this. What's the problem with this now? We talked about the good thing. The good thing, single search if you're using the ID or MongoDB, right? If you're looking up a document by its ID, it's a single beautiful search. Immediately find the document, basin document, right? And if you're lucky, you're gonna find anything in next to it, right? It's not just one document. This is a collection of documents in a single page. I gotta find out what's the page size in WireTiger, right? But this is what you get. You're gonna get this, and it's gonna be cached in memory temporarily, right? So if you're lucky, the previous ID next to it is also, you're gonna get that as well, right? If the sequence really makes sense here. The problem, though, my friends, is now let's go back to the secondary indexes. The moment you introduce it, now this becomes identical to MySQL. MongoDB after 5.3, if you choose to be a cluster connection, it's almost identical to MySQL now. It's identical to MySQL. The ID field which is the primary key, is the cluster index. The secondary indexes point to what now? They have to point to the ID, right? There is no record ID. You moved where the data is, right? Previously, the secondary index, and I should have drawn this, but sorry, I did not. The secondary indexes used to point to this thing, the hidden, which is a very tiny value, record ID, 64-bit. That's it. You know how large is the ID field? And did I actually mention that? Let's go to the object ID. I actually mentioned it. Someone highlighted it. 12 bytes. Dude, this is bytes, not bits. This thing is a 12 bytes by default. And it has like the first 4 bytes is the timestamp, the second 3 bytes is I don't know what. This is because Mongo decided to scale first, right? And so they wanted their IDs to be unique across machines. So even the second 4 bytes is a combination between the process ID and the machine name, and so the ID is truly universally identified across machines. So that's why it's so big. 12 bytes is so large. Yeah, so it's 12 bytes compared to 8 bytes, right? Because 64-bit is 8 bytes and 12 bytes is 12 bytes, right? So 4 bytes extra. You might say, who cares? 4 bytes extra. But here's the thing. Here's the thing I didn't know. MongoDB actually allow you, and those who use MongoDB more might know, you can actually set anything in the ID field. So it's a user-controlled field. If you don't set an ID, it's going to generate one for you. But if you do set it, you can have it to be a very large. People can have crazy ID values. And guess what? The secondary indexes now has to point to the ID because that's where the data is. And that's where all the problems of MySQL arise, where if the ID is a poorly chosen value, if the primary key is a poorly chosen, like a GUID, right? Again, there's a lot of course, discussion about having a UUID as a primary key, but we know it's very large. If you use it as a primary key, then those primary keys are stored in the secondary indexes as values. And that's what bloats everything up. So now the secondary indexes just blow up, right? And that's basically the evolution of MongoDB, you guys, right? As a summary, we started with mmap, right? Moved to WireTiger, gain a little bit of new features, but introduced new problems. For Sync 5.3 and 6.0, you can actually do clustered indexes. Gonna see you in the next one. You hope you enjoyed this video. Goodbye. Discord has posted a new blog a few days ago about a very interesting problem they ran into. How they store trillions of their messages. If you don't know, Discord is this client messaging app that has become really popular, especially in the live streaming, I think, a space where most of the gaming and live streamers use Discord as their, de facto communication channel. So for chatting or audio calls, and I've seen sometimes I watch YouTube podcasts that use Discord as calls to receive calls. So they have discussions there. So it's a very popular app. And I think 2017, I covered how they moved from MongoDB as their primary storage to Cassandra. And it was a very interesting blog that they wrote back then. And just a few days ago, they wrote another blog, how they storing trillions of messages. They moved from billions now to trillions. And they are moving essentially from Cassandra as their main storage engine and database to CellaDB. In this blog, what I want to go through is I want to go through the sections that they talk about. They talk about the problems of the Cassandra. They talk about the challenges they face. They talk about many other things. And then they talk about what they did to solve these problems and migrate everything from Cassandra to CellaDB. So let's analyze this. Let's get started. How Discord stores trillions of messages. In 2017, we wrote a blog post on how we store billions of messages I talked about that. I'm going to reference the video below and the podcast as well for those listening. We shared our journey of how we started out with using MongoDB, but migrated our data to Cassandra because we were looking for a database that was scalable, fault tolerant, and relatively low maintenance. So those were the things they were looking at. The reason they didn't start with a relational database is they wanted a distributed database to start with, scalable. That's the word they used. I want to talk about this a little bit. As relational databases, while you can shard them, you can definitely partition relational data into multiple instances. It is commonly the case where that causes you more problems. The reason is, simple reason is just transaction. You can't do transactions across shard effectively, right? Because transactions are by design, the multi-version concurrency control aspects of it and acidity and all these nice properties are just at the instance level. You can't just spread them. Now, I know people yell at me, yeah, you can, 2-phase commit, 3-phase commit, and Paxos and Maxos. Of course, there's always a way, but at its simplicity and so predictability, as a single instance, all the data is in one instance. Now, that doesn't mean you have to use one instance for a relational database. You can scale horizontally by having replication, have one master writer that receives writes, and then have many read replicas. And as the master node receives writes, the wall changes or the transaction log changes will be pushed down to the replicas. And the replicas will have the essentially eventual consistency, sort of speak, and they will catch up. So that's the state of the art that we have it, and you can go further than that and shard if you want by actually splitting the data into multiple databases. In that model, in the original model, everything is in those replicas. All the data is there, and there is no, oh, this database has only half of the data and this database has the other half. No. If you want, you can shard that by partitioning and put the data based on a certain sharding key. And if you hit that sharding key, you hit that instance and you read the data that you want. Right? MongoDB by default and Cassandra and Scala, they start with that model, that sharding model, where things are partitioned, things are fault tolerant, things are scalable, right? As they call it. And this way you have the database, the nodes will have fewer and fewer data. As a result, your queries are faster when you hit that. The reason is, as I always say, the goal of all these queries is to work with as fewer data as possible. That's the goal. Yeah. Instead of searching trillions, right, you search sub-millions. And of course, if you work with fewer data and you have beautiful indexes, you can even further reduce that result set into exactly what you want. That's the whole trick behind databases. Right? Work with as fewer data as possible. How do you get there? Indexes, partitioning, sharding, all these tricks. So MongoDB, Cassandra does that by default. You have a partition key, and based on the partition key, you hit the node, and that node has the data, and the node, of course, that becomes, of course, dangerous, right? Just one node have part of the data. What if that node dies? That's why you have a quorum of this data should be duplicated in multiple nodes, usually 3. And of course, that's basically the state of the art as we have it. All right, with that said, we wanted the database to grow alongside us, but hopefully its maintenance needs wouldn't grow alongside our storage needs. Unfortunately, we found that not to be the case. Our Cassandra cluster exhibited serious performance issues that required increasing amounts of effort to just maintain, not improve, right? So let's unpack that. We store our messages in a database called Cassandra Messages. This is their database that stores all the messages. In 2017, we ran 12 Cassandra nodes storing billions of messages. That's when we discussed this article back then, right? At the beginning of 22, we had 177 nodes. So they increased a lot, right? To store trillions of messages. Trillions, we're talking about multi-thousand billions, right? That's nuts. To our chagrin, is this even a word? What the heck is chagrin? Distress. Okay, I never knew that word. To our stress, it was a high toil system. Our on-call team was frequently paged for issues with the database. Latency was unpredictable, and we were having to cut down maintenance operation that became too expensive. Why? Why is latency unpredictable? Well, let's take a look. There is a SQL statement here, CQL statement, that has been chopped, I think, by the Safari reader. So I'm gonna show it here instead and then go back there. I prefer that view is better, but here we're looking at the messages table. Their message table includes the channel ID, which is a unique identifier for the channel and the server. Bucket. A bucket is literally an integer that represents a time window. Very critical to let you know that this message lived in this time window, because you're going to have a lot of messages in the same time window and you want them next to each other usually, right? Especially if they are belonging to the same channel. Why? If you do a read to read certain message at a certain time, most probably you want to read those messages that came after and before it, right? Unless it's like direct messages, that should be in a different system, right? But if it's a public channel, and just a channel, messages from that channel should live together. Why? Especially in time, because a read, if I do an IO, that's true for both B3s or LSM that Cassandra uses, or CellID for that matter. You want to do an IO and you want to get as much as from your IO as possible, right? You don't want to do multiple IOs to read 10 messages. You want to do a single IO and get 1,000 messages, 20,000 messages, if possible. Just all compactly nice into a single page. That's the goal of databases. If you manage to do that, you won, right? And that's what they are doing. They're doing it. The data modeling is beautiful here, right? And they have also a message ID, which we're going to talk about in a minute, that this ID, this is a unique identifier that identifies this message and the author and the content of the message. And notice that the primary key is on the channel ID, sorted by the bucket, and then the message ID. All of the three are the unique primary key, which is then defines the clustering of that table. And the clustering is very critical because that's how the data is stored on disk, based on this ordering, the channel, bucket, and message ID. Sweet. All right, now we can go back to the better view here. So the CQL, the Cassandra query language statement above, is a minimal version of our message schema. Every ID we use is a snowflake. All sequences is not, it's all just monotonically increasing. You don't get a lot with it. You don't do much with it. You want more data in your messages, such as time and other information, right? And that's what a snowflake gives you here. So what do they do with the snowflake? Why don't we just use UUIDs, GUIDs, right? GUIDs are unique, which is nice, but they are random. Random is not good in storage, because if you generate random messages, they have no relation to each other. And as a result, the database, if you cluster on that UUID, it will try to sort it. And the sorting does not make any sense because the thing is random. So if you turn around and try to read these UUIDs, you'll be going all over the place. So there is a better version of UUID, which is called the ULID, how do you pronounce that? Lexicographically sorted GUIDs. that is used now by Shopify, and I covered that it gives you like an ordered list that are unique UUIDs. Beautiful. So if you generate UUIDs that are next to each other, they are technically ordered. And if you have ordered things that are relative to each other, a query to give you one UUID will give you anything related to it also in the same page. And if you do that, things that are next to each other will make sense, right? And that's what Shopify did. Shopify used this to ensure idempotency in their ordering. Every order request will get a unique ULID, and because we know that orders will be absolutely next to each other, right? One after the other, right? They are storing these orders and these requests, and if they want to check if the ULID is a duplicate, if the order is a duplicate, they just read that, and guess what? They're gonna always hit that neat tail page where all the UUIDs must live, and this page will be cached, right? It's almost impossible that you're gonna hit a request order that has been submitted 3 days ago, right? Because orders, to check duplicates, you only check within a few seconds or even minutes, right? And those will be guaranteed to be next to each other. And that's the beauty here. So they're using something similar here. They are trying to cluster, they're trying to group things together. We partition our messages by channel they are sent in. So that's the first key they use to partition, along with the bucket, which is a static time window. This partitioning means that in Cassandra, all messages for a given channel and bucket will be stored together and replicated across 3 nodes. This is the quorum, right? The replication factor. Every message within the same channel and bucket, if you send a lot of messages in the same time window, all of these nice messages will go to the same nodes effectively, right? Within this partitioning lies a potential performance pitfall. A server with just a small groups of friends tend to send orders of magnitudes fewer messages, of course, than a server with hundreds of thousands of people. And in the same time, same channel, right? In the same channel, same group of time, you will get a burst of massive amount of messages from one server compared to another. So you'll see these, they call hotspots, like one bucket of time, especially like maybe at night-ish, right? You would see this flood of queries into these areas and writes, right? And if this happens, this will create this hotspot. So why is this a problem? Let's continue reading. In Cassandra, reads are more expensive than writes. So in order to talk about this, we need to understand the difference between what Cassandra uses, which is a log structured merge tree, versus which most all relational databases use, which is B+ trees. B+ trees are data structure that is used to index your table, and they can also be used to store the raw data as well, sorted into what we call leaf pages. So each page will have, based on your primary key, I'm assuming a clustered index primary key here, all your primary key and the full row will be stored in these pages, ordered. So row number 1 and all its columns, row number 2, all its column, 3, all its column, right? And it's going to be ordered until the fixed page is full, and that becomes one leaf page, and then followed by the next one. And these leaf pages are linked and changed together, so you can traverse back and forth between the list pages. Then you have the root node, an intermediate node that is allowed to be used to index, to quickly go to the page which has the row you're looking for, right? Very simple. If you're looking for row number 55, you'll start with the root node, and the root node will tell you, oh, if you want row 0 to 10, go to this page. From 11 to 20, go to this page, and so on. So 55 is between this and this. You hit that page, and then you do in the internal node, you do the same thing until you hit the leaf page that you want. That's how B+3 works in a nutshell. And in unclustered indexes, the leaf pages will not have actual data. They will have simple pointers to the actual table. Like in Postgres, it's the tuple ID, which is a page ID, and the index of the tuple. But in a MySQL or other databases, it's a pointer to the primary key. It's the primary key value. Right? And how do you do an insert? Very simple. You want to insert a row, you need to find which page that row needs to go in that index, and then insert it right into that page. And you will update it in memory, of course, that leaf page, right? If hopefully there's a space in your page, and you're going to write it right there in the correct order. So let's say the values are 1, 2, 7, right? And then you want to insert the value of 3. 3 has to be right after the 2 and right before the 7. You have to order them as you insert. The order is critical, right? Because it's clustered. Indexes are, at the end of the day, they have to be ordered. And when you do that, you also use a persistent model such as the write ahead log or the commit log, they call it transaction log, to persist these changes only into that, and then you commit that. It's enough to commit just that. You don't have to flush the page to disk, right? But eventually you will have to. In B+3, if you flush the page, it's an update. It's an actual physical update to the OS. It says, hey, this page, go and update it. And what does that mean? Well, the page is a fixed size. It lives on disk, on a file, and it lives really in a particular offset, and it ends at a particular offset. So you would issue a write and say, hey, write this content, this new content, on position number 2000 for 8 kilobytes. That's like an example of a fixed page, right? Or 16K in case of MySQL. And that's an update. Right? So what's wrong with updates? Updates are like in-place updates. In the days of hard drives, this is an actual in place. So when you do that, the hard drive will seek in and will find the location sector and then write it back, overwrite whatever you had. In SSDs, unfortunately, there is no thing as called in-place update. You don't just overwrite things, unfortunately. That's because of all the NAND, the way NAND works, NAND cells. You invalidate. To write something to the SSD, to update something to the SSD, you know the logical block address, right? Which is basically what maps the file system offset down to an array, if you will, a list of logical block address. And those will be flushed to disk, right? This is what I want to update. That will translate into whatever technology in the driver, whether this is NVMe or normal SATA stuff. So yeah, in SSDs though, when you do an update, do you want to update a certain LBA, what happens is you can't overwrite existing things. So what the SSD controller does is actually takes your write, right? Write it to a new place, finds a new block and a list of pages where this fits, and then writes your data. The second step is it invalidates the old data. That's what it does. It says, hey, this is no longer valid there. So that's another write. So one write, two writes, one write to actually write the thing, the second write to invalidate it, and the third one is an in-memory DRAM change, which now points your logical block address in the OS that the OS uses down to the new physical location. That's what we change in the SSD. We change the pointer. The pointer is now this. This is your new pointer. This way the OS can continue working with the same LBA, the logical block address, but the physical block continues to change. And that's what happens. Every time you update, It moves to a new place. It moves to a new place. It moves to a new place. This is a disaster if you keep doing it a lot. Why? Because now you're left with stale, invalid pages. Eventually, if you do it a lot, then you will fill up your SSD very quickly with invalid data. Right? Especially if you update a lot of stuff. So you'll have active and invalid, active and invalid. So now what happens? This invalid data, to be used, it has to be cleared. And guess what? To be cleared, the whole erasable unit has to be erased to be written to. You can't just use it. And that in itself is an expensive operation called the garbage collection. So as you want, all of a sudden you want to do a new update or new write, you have no place. So the controller will say, wait a minute, let me find a stale block, erase it, that's one write, and write your stuff to it. So that's, you're gonna do 2 IO in this case. Not bad, right? But here's where it goes really bad. When you have an erasable unit, and I know I'm going all over the place, but it's all related, guys. Believe me, it's all related. That's why we do these deep dives. Like, well, if you're gonna do like a summary, why would we be here even, right? Let's talk seriously about these things. And if we have this erasable unit, and if it has mixed valid data and invalid data, this is where it gets really bad. Because now I can't just erase it, it has valid data. So the controller has to garbage collect, and this garbage collector has nothing to do with Java or Cassandra's garbage collector, has nothing to do. This is the SSD garbage collector. The garbage collector. Keep stumbling by my words there. So now the garbage collector have to move the valid data to a new block. That's one IO. It has to erase the block, a second IO. It has to write 3 IOs. Your write throughput, and as they call it, the write amplification, is tremendously increased. Your 1 IO that you think it's a single update, it's now 4 updates, 4 IOs, which now, of course, this takes space from, first of all, it takes bandwidth. The IOs now being used for things that you didn't really, it's not your things, it's the system things. And then you also need a space to store this temporary data, right? That's the over provisioning. So that's kind of a quick lesson on SSDs and how updates are really not quite good on the long runs. That's why B+3s and SSDs, and especially like if you have like page splits, this become exacerbated. And as you grow the tree splits and pages splits, and all of these splits are just updates, right? It's like more writes and updates and deletes and updates. So like that's where things go really bad when it comes to SSD. And when I say really bad, you're talking about years until this can, you see the difference, you know? So people invented this concept of log structured merge trees, or LSM, which Cassandra is used by default in ScyllaDB, right? And now what the main goal of the LSM is, everything is a write, immutable. You rarely do an update. You're going to do an update, but very rare. It's called a step called compaction, right? So always write in memory, write to the commit log, write to this transaction log as you do changes. Everything is a write. And as you're in memory, the mem table is filled up, you flush the mem table to disk as a called the, no, you don't flush it directly, you sort it and then you flush it as a table. And this is called the sorted string tables or SS tables. So you sort and flush. So when you flush, you write. You never ever update this table. Never. It's always an insert. So now this, as you create more and more SS tables, this first level gets filled up. So what you do is the next step, you read a bunch of these tables based on certain criteria and write them to another larger sets of tables, right? And then you do the same thing. And always, everything is an insert. Everything is an insert. What this creates is now, the problem with this is, let's talk about the good. The good about this is, as you writes are extremely fast. The SSD doesn't have to do this, right? Everything you're writing is actually your data. You're not really invalidating anything, right? Like, you're always writing in a new place, which is a nice thing, especially if you're writing in sequence. Database SSDs love this, right? It's a very nice sequential writes if you do it sequentially. But like, think about what do. We insert, we update, like the users do an insert and update and delete. All of these will be translated to inserts. All of them. An insert is an insert in an SS table, in an LSM. An update is an insert. A delete is also an insert. It's called a tombstone. You create a tombstone. Right? So if you keep inserting and updating a message and updating the same message, updating the same message, update, what you do is, like, you create new records effectively, right? And you persist them in new SS tables and SS tables. So now, to look for the thing you actually want, reads have become very, very slow, because they have to first look up in the in the mem table, and then you look up in the first layer of the SS table to look for your stuff. You go, if you didn't find it, you go to the another SS table, and you go to another SS table, you go to another SS table until you find what you were looking for, right? Or you found a tombstone that, this thing is actually deleted. I have to stop. Well, both Cassandra and Scylla uses a technique called Bloom filters. Says, okay, your record is actually it's impossible to be here. So it's like a nice bitmap that is stored that you can quickly check to use to see before you actually open the SS table, to check if this thing is actually there or not. Right? So these are like kind of nice trick. With those explained, now that we know the benefits of LSM versus the detriments, now reads have become slow, right? So what we do with the LSM is we do something called compaction, and this is where updates and deletes happens, where we can group things together and then delete the tombstones, delete duplicate records, have one record of the same thing. We don't need the old stuff anymore, right? Remove it. You have compact things. So 1,000 version of the same thing are no longer the 1,000, it's just one. You delete this stuff. And of course, in that process, what you do is you create a new thing and you just delete, right, the old stuff, and you create. It's always a create a new one, right? So a delete technically is a marking and that LBA in the SSD as deleted, but it's not as, you do it you don't do it as often as an update to a B3. Does that make sense? That's the goal of it. SSD. I personally can't speak to how bad B+3 can affect your SSDs, or LSMs. Like, I only hear things, and I don't believe anything I hear unless I actually see it myself, So that's, we always, human beings, we have a problem, we create a solution, but that solution almost always creates other problems, and that's what we have here. All right, with that rant, now let's jump into it again. In Cassandra, reads are more expensive than writes. Writes are appended to a commit log, as I talked about it, and written to an in-memory structure called a mem table that is eventually flushed to disk. Reads, however, need to query the mem table to potentially multiple SS tables on disk files to find what you're looking for. So this is a more expensive operation. Lots of concurrent reads as users interact with servers can hotspot a partition. Okay. Which we refer to as imaginatively as a hot partition. The size of our datasets when combined with these access patterns led to struggle for our cluster. So what happens here is, because most queries go to almost the same partition, almost to the same bucket, channel ID, will create these hot partitions. Like the node becomes so busy because all the queries will go to it. And this is the same tail problem that we talked about, where things that are, which is a good thing when it comes, if the database has a good caching, in place, it should just serve you from the memory, because these should be in memory. But because this is LSM, it has to go to disk because nothing is in memory. Can't put these SS tables in memory, right? They have to live in disk, apparently, right? I don't know much about LSM, but if this was B-tree, the page will be just right there, alive for you. The page will have everything. There's no walking to get multiple things. It's just one thing, You get the page, and that page will give you everything. So it's actually a better design if you have these hotspots, because all these hotspots will hit that cache, right? Versus in this case, you're doing more IOs because you're doing SS tables. Now you might say, I was saying, let's just compact. You can't compact fast enough to go with the demand, because these are brand new things. As they are written, people want to read, right? Because if you write new things, what the moment you write a message, what is the first thing you're gonna do? Other clients want to read that same message. In a relational database, this is the best case scenario, right? Because you just wrote something, it's hot in memory, it's sure, it's dirty, but we're gonna serve you that read from the buffer pool. It's right there, take it. We don't even need to see the disk. That's the power, right, of B+ trees essentially here in this case, right? But in that case, what we have, I know I'm repeating myself, but in this case, what's happening is, because we're doing this SS tables and writing to another SS tables and taking just to make writes fast, we significantly slowed down reads. And that's the main problem here. When we encountered hot partition, it frequently affected latency across our entire database. Our channel and bucket pair received large amount of traffic, and the latency in the node would increase as the node tried harder and harder to serve traffic and fell further and further behind. It just can't keep up. One node can't keep up. If all the traffic goes to one node and the node has to do I/O, if the node is cache, if it's like serving from the cache, sure. And even that is a lot, but doing I/O and serving and doing compaction, good luck. So far, this is a problem with both Scala and Cassandra. This is not a unique problem for Cassandra. Since we perform read and writes with quorum consistencies, all queries to the nodes that serve the hot partitions suffer latency increases, resulting in a broader end-user impact. At the end of the day, users feel it. Right? Cluster maintenance tasks also frequently cause trouble. All right, so there's a maintenance operation also causes some more trouble. We were prone to falling behind on compactions. That's the problem, right? I told you, human beings, we always introduce a solution, but the solution has problems. Compaction. When did we ever had to do compaction with B+ trees? Never, right? Where Cassandra would compact SS tables on disk for more performant reads. Not only were our reads then more expensive, but we'd also see cascading latency as the node tried to come back. I talked about that a little bit, right? And here's they talk about the garbage collection of Cassandra, which is a valid point, right? Let's talk about that a little bit. We frequently performed an operation we called the gossip dance, where we'd take a node out of rotation and let it compact without taking traffic. And so they took it out of rotation, so it can't receive any writes anymore. Let it compact, right? I don't know what happened with quorum now. Like, do you add other nodes, I suppose, for the quorum, right? Bring it back in to pick up hints from the Cassandra hinted handoff, and then repeat until the compaction backlog was empty, right? So it can start compacting. So that's kind of a way to speed up compaction, because the compaction can't keep up. All these SS tables are just being written. We also spent a large amount of time tuning the JVM garbage collector and heap setting, because GC poses would cause significant latency spikes. That's understandable. As you write to, because Cassandra is written with Java, and Java is a garbage collection language, and as you write new things to create memory entries in the heap, especially those large mem tables, if you go out, if there are no pointers to this, no stack pointers pointing to this heap at all, then the garbage collection wakes up and start removing all this entries, all the memory, all the unused memory, right? So it can be released back to the operating system. And those garbage poses, it has to pose, because technically what is the garbage collection has to acquire a mutex, I suppose. I don't know much about garbage collection, but I think that's what I know, basic thing about memory and operating system, right? Has to acquire a mutex to release anything in memory, and that poses, as you want to allocate more memory, can hit a page that you're about to write to, and that's when the poses happen. A memory page, that is. And that's the garbage collection poses is what caused linker D, right, to move from Java, that's the service mesh reverse proxy, to Rust. They moved to Rust because they say, hey, we want just a garbage collection free, because we want predictability, right? So they moved away from Java and Rust, and they saw significant performance. And that's a valid criticism of Cassandra, and I totally understand that. The rest of the I/O stuff, I don't see how Scala is better. Well, you can argue that, okay, changing our architecture to Scala, well, we're going to use C++ because Scala is written with C++, and there is no garbage collection in C++. That's nice. That's fast. But how is it better, right? How's Cassandra, how's Scala DB better? And I don't know the answer until I actually research both of them and see how exactly they are. To me, maybe the compaction strategies are different. Maybe there is a specific enterprise level in Scala that is having certain features that is not available in Cassandra. That might be the case, but it's not mentioned here. So let's continue reading. Changing our architecture. Our messages cluster wasn't our only Cassandra database. We had several other clusters, and each inhabited similar, though perhaps not as severe, faults. In our previous iteration of this post, we mentioned being intrigued by ScalaDB, a Cassandra-compatible database written in C++. Its promise of better performance, faster repairs, stronger workload isolation via its shard pair core architecture. So that's an interesting thing. So each shard live in its own CPU core. That's how it works. And a garbage collection free life sounded quite appealing. Although ScalaDB is most definitely not void of issues, I love that they mentioned this. Right? It's not really defensive here. It's a void of garbage collection since it's written C++ rather than Java. Right? Historically, our team had many issues with garbage collection with Cassandra, from GC poses affecting latency all the way to super long consecutive GC poses that got so bad that an operator would manually reboot and babysit the node back to health. Wow, that is really bad. If a node just dies because the garbage collection can't keep up, that's really bad. I understand that, right? These issues were a huge source of an on-call toil and the root of many stability issues with our messages clusters. Okay. After experimenting with ScalaDB and observing improvement in testing, we made the decision to migrate all our databases. While this decision could be a blog post in itself, the short version is that by 2020, we had migrated every database but one to ScyllaDB. Okay, so everything they migrated except the Cassandra message, the actual core database. Why hadn't we migrated yet? To start with, it's a big cluster with trillions of messages and nearly 200 nodes, which 177 in particular. And migration was going to be an involved effort. Additionally, we wanted to make sure our new database could be the best it could be as we worked to tune its performance. We will also wanted to gain more experience with Scylla in production, using it in anger and learning its pitfall. We also worked to improve ScyllaDB performance for our use cases in our, okay, so they talk about that, how they are actually improving Scylla itself. Because again, Scylla by itself, if you just didn't do anything and you just implement Scylla, I suppose you're gonna get slightly better performance, but the hotspot thing is identical. Scylla still can't compete. You can't keep up with the amount of writes at the tail. And all these writes are going to multiple SS tables that you will turn around and issue many reads, because that's what the clients do. Discord, what do? You write a bunch of messages and you turn around and read the same messages. That's how Discord works. Because you're reading at the tail is dirty. The tail is spread all over the place. It's not just in memory. It's in this table and this table and the table behind it, right? So you have to do many reads. So the ScyllaDB, and that's what they did not mention. If they just blindly replace Scylla with Cassandra, that will not give them much performance. That's my opinion, I think. But they didn't do that. They actually did more work. What is that? And they mentioned that hot partition can still be a thing in ScyllaDB. And so we also wanted to invest in improving our system upstream of the database to help shield and facilitate better database. So they knew, right? So I take that back. They knew replacing Scylla blindly with from Cassandra to Scylla, they're still gonna be the same problem, right? We're still gonna have this hot partition at the tail. So that's not, no, we're gonna need to change our architecture. So what did they do? They introduced an API, I think. Data services, serving data. So now, and this is an interesting thing. How do you actually read? Right? We don't know much about that. So let's talk about that a little bit. How does Discord read from Cassandra or Scylla? There's an API, right? Does the API has any caching whatsoever? No. What they did here is absolutely brilliant, and I absolutely love it. Let's talk about it. With Cassandra, we struggled with hot partitions, and you're gonna struggle with Scylla. Let's be honest, right? Even if you did Scylla, you're gonna have hot partitions. It's the same identical problem. It's the same architecture at the end of the day, right? High traffic to given partition resulted in an unbounded concurrency, leading to a cascading latency in which subsequent queries would continue to grow in latency, because like it just can't keep up, because that node is busy reading 700 SS tables, and the read after that is just queued in, and the OS will have to do the read, and the OS will try as much as possible to combine these reads. That's how the file system starts to work, as much as possible to combine these IOs, but it still can't keep up. The bandwidth of SSD will be just, completely saturated. If we could control the amount of concurrent traffic to hot partitions, we could protect the database from being overwhelmed. How? To accomplish this task, we wrote what we refer to as data services. Nice. Intermediary services that sit between our API monolith and our database cluster. Interesting. So now they have something called data services. They didn't have that before. What does the data service do? When writing our data service, we chose a language that we've been using more at Discord, Rust. Okay, we get it. Rust. Everybody loves Rust, right? The language should make it easy to write safe concurrent code. Its library also were a great match for what we were intending to accomplish, right? And then the concurrency here is the most important thing. They want building as an asynchronous I/O, and the language has a driver support for both Cassandra and ScyllaDB. Our data services sit between the API and our ScyllaDB clusters. They contain roughly 1 gRPC input per database query and intentionally contain no business logic. Good. The big feature our database services provide is request coalescing, which is basically, think of it like grouping. And that is the key here. Look at this beautiful diagram. For those listening, we're looking at a for request or n number of requests to the same identical message, right? Or not message, like, yeah, message ID, same bucket, same channel. So all of these, usually they used to be 4 concurrent different read requests to Cassandra, right? Now they built this intermediate layer that receives all these requests and they coalesce them. So if multiple users are requesting the same row at the same time, we'll only query the database once. The first user that makes the request causes a worker task to spin up the service. Subsequent requests will check for the existing of that task and subscribe to it. Wow, that is a beautiful design. That's like amazing. Kudos. Absolutely love it. That's pretty cool. So here's my point. I wonder what happens if they did implement this with Cassandra. And I'm not saying just don't move from Cassandra, sure, just don't move it. How much would you guys would have saved? Right? Would Cassandra hold up? Or will the garbage collection poses will still kill us? And that's the question I couldn't answer. Right? And I suppose that will remain unanswered, right? I suppose, of course, now their configuration is way more optimal because they went all the way, right? They changed the architecture to include this intermediate layer to cache almost. Like you can use this as a cache. They didn't talk about that, I think, but you can coalesce requests so you can group and send one request, but then at the same time, you can cache results, right? This worker task is so brilliant, this idea of a worker task, because it will be in memory and you can, as long as it's alive, that means someone has just made the request, right? Here's another example. Let's imagine a big announcement on a large server that notifies everyone, right? Users are going to open the app and read the message because now someone just writes one message, 100,000 people reads the same message. Everyone sends the same request, right? So all of these requests to the same single message, right? How do they know the message? I suppose it's going to be a notification. You get the notification ID and then you send a request to get the message, right? Okay. And then now you have the message ID and now everybody sending flood of queries. In the old system, those were 100,000 queries. In the new system, it's a single? I don't think it's just going to be single. It's still going to be multiple, probably, right? Previously, this might have a hot partition, and on-call would potentially need to be paged to help the system recover. With our data set, we're able to significantly reduce traffic spikes. Yeah, it's not going to be a single one, like 100 million, because it's a worker, right? It's a worker subscriber thing, where the first person who made the request will create this worker and then send a message, while all of these queries at the same time concurrently, we're going to look up this worker, and as long as the worker is executing, you're going to hook to it, right? But what happens if the worker is get the response and writes? Is the worker dead? Do we cache the worker result for subsequent queries, or do we create new workers every time the old worker is dead, even if it's the same request? The second part of the magic here, and this is truly magic, I absolutely love it, is upstream of our data services. What do you guys do? We implemented consistent hash-based routing to our data service to enable more effective coalescing. Whoa. Right. Because remember, load balancing. If you want to, like, that's the problem, right? I didn't think about that. See, if you have like a if you have load balancing in place, then these data services you'll have multiple data services, right? Requests from different clients across the world will go to different data services. And in this particular case, you will not hit, the chances you're going to hit a data service that happened to cache a coalesced request are very low. So how do you then, this is genius. This is absolutely genius. I love it. So what they did is they took, and the load balancer, and again, I didn't read this part. I think I skipped about it. Now I'm just reading it for the first time. Now the load balancer, they have like a hash based to take the request and says, okay, you're going to channel X on this server. I'm gonna hash you to this data service. Yeah, it's gonna create more load on this particular data service, but it's good. You're gonna hit that cache. The chances of request coalescence are higher. Brilliant, just brilliant. I love it. The improvement help a lot, but they don't solve all the problems. Okay, they have more problems. We're still seeing hot partition and increased latency on our Cassandra cluster, just not quite as frequent. Wait a minute, Cassandra cluster? I thought you moved to Scylla. Why does it say Scylla here? That's so confusing. Just not as quite as frequent. It buys us some time so that we can prepare our new optimal Scylla DB cluster and execute them. So that's what confused me. All right. So I take everything back. So it seems like they did the data service before moving to Cassandra, right? Again, as I'm reading this, I'm discovering new things again, right? I apologize if I made a mistake. It's not clear because the graphic shows Scylla messages, yet the way they are talking about it is they say, okay, we're still hitting Cassandra. Okay, all right. So the data services are hitting Cassandra, and still they did a lot of good things. Right? So they improved, but still they have problems. We're still seeing hot partition and increased latency on our Cassandra, just not as quite as frequently. Nice. It buys us time so they can move. Okay, so they still saw the increased latency and hot partition even with all of this, right? Even with request coalescing, even with hash-based grouping of the request, so they hit the same data services so they can take advantage of this request coalescing, right? A very big migration. Now they're into the migration. Our requirements for our migration are quite straightforward. We need to migrate trillions of messages with no downtime, and we need to do it quickly because while the Cassandra situation has somewhat improved, we're frequently firefighting. Okay, so that is the case. So they did do the data services, they did do the request coalescing and all this on the Cassandra. And that the screenshots confused me. That's what confused me, because it says Scylla messages, and I assume they moved to Scylla already by that time. Okay, so that's actually good. So what are the remaining hot partitioning and latency? Are all of the remaining problems, are all the garbage collection? Really? That's it? All right, let's take a look. Step 1 is easy. We provision a new Scylla DB cluster using our super disk storage topology. By using local SSDs for speed and leveraging RAID to mirror our data to persistent disk, we get the speed of attached local disk with the durability of a persistent disk. With our cluster stood up, we can begin migrating data into it. Okay, so they built a brand new cluster with a completely different architecture than they had with Cassandra. Maybe that helped a little bit with the I/O, I suppose. Our first draft, because it's still, even with with request coalescing. What are you doing? You're minimizing the number of requests. I wonder what will happen if they cache the data, they cache the messages, or even at least the pages. I don't know if the concept of pages exists in Cassandra. Better be. It's the same concept as a database at the end of the day, right? And why not cache? The problem, I think, clearly is like editing. If you edit a message, then you have to invalidate all that cache, right? And that's the big problem. And I think Twitter, I know a lot of people are just